what we are looking at here is a simple demo on a very synthetic data set that allows us to represent the curves. So as usual, I'm running some imports of some basic modules. Scikit-learn, sklearn should be your favorite module in this class. This is the one that contains a lot of the machine learning functions that are already implemented. And I'm going to generate the same data set that I played with last time, which is based on essentially Gaussian distributions to create a distribution of points that have some overlap. So I will not go over it again, but essentially this is what it looks like. So we have two blobs of points, the red points and the blue points that have some partial overlap. And the goal here is to understand whether we can generalize or not. Now, if I want to talk about generalization, and I need to fix the set H that I'm using, the set of hypotheses. And what I'm going to use here is I'm going to use the set of nearest neighbor classifiers. Okay? Now, nearest neighbor classifiers are a bit hard to describe in terms of a finite set of hypotheses H, but they're convenient to use. They're one of the simplest classifiers out there. So I'm going to use them, and you'll have to accept that I don't make a one-to-one connection with the very theoretical model that I built last time. So what I'm going to do here is the following. I'm going to create new data, and a lot of them. So I'm going to create about 10,000 new data points that I'm going to use as a proxy to evaluate the true risk. Okay, so said differently, I'm given a data set. The data set is what we're plotting on that little plot here. It contains both red points and blue points, and this data set doesn't have too many points. Okay, that's what I'm using for training. Now, if I want to test, I'm going to generate a new data set, if you wish, that has many more points. I can do that here because my example is synthetic, and I'm going to use the empirical risk on the new data set as an approximation of the true risk. Okay, so why that's a good approximation? I'll defer that discussion to the course on cross-validation, and you'll have to accept that it's my way of estimating the true risk. Now, with that, I will be able to compare the empirical risk that I obtain on my data set with the true risk that I would obtain if I were to average many times on unseen samples. And what I'm going to do is I'm going to use a k-nearest neighbor classifiers, which is a simple classifier we'll discuss again in more details later today, that assigns a label based on the labels associated to its k-nearest neighbors and taking a majority vote. But I'm going to change the value of k that I use to select the k-nearest neighbors from 1, single nearest neighbor, to 191. The reason these are odd numbers is because that's something required by Scikit. Now, if I do that, I'm going to run the simulation, and the simulation works. It's going to take a little while. As you can see, there's a progress bar, and that's because for every value of k from 1 to 191, I have to generate a simulation that estimates the empirical risk and that estimates the true risk. So we're almost there. All right, here we go. And now based on that, I'm going to plot the curve. And this is what we observe. So as you can see, it's not perfect, and that's because I'm using a specific data set to plot that curve, but you see the following trend. I'm plotting here the testing error, or the risk, if you wish, as a function of the k-nearest neighbors. And if you look at my x-axis closely, you'll notice that I flip the order. It goes from high values of k to low values of k. And the reason I'm doing this is because the value of k is inversely proportional to the richness of the class. A large value of k means you're using a lot of nearest neighbors, will impose a classifier that is very constrained. It's going to have a smooth decision boundary, so it's like it's not very rich, whereas a small value of k will allow a much more jiggery decision boundary, which corresponds to a very rich class. Now, if you compare the curve in orange, which is the empirical risk, with the curve in blue, which is the true risk, you'll see that we get exactly the behavior that we were expecting, in that the empirical risk is always decreasing, eventually reaching 0 when you're only using one nearest neighbor. If you look at the blue curve, it starts decreasing until it increases again. And the value that seems to give you kind of the optimal value of k to choose from is actually about, in that case, 30, I believe. And we'll again revisit that much more seriously when we study these problems in more details in the context of cross-validation. Again, this is just an illustration on a very synthetic example, but the whole point here is to show you that that curve that I'm just sketching and that we try to provide based on the analysis field of path learnability is actually very real. And you will be able to observe it in many, many different contexts, especially when you look at deep learning on mega huge data sets, for instance.